discussions today. Now we have Bill Coish from Canada. We'll talk about charged magnons at the surface of a topological insulator. So, Bill, welcome.
Thank you very much. Yeah. Thank you very much to the organizers for letting me come to this conference. It's been really very nice so far. So obviously the venue is amazing, and the talks so far that I've seen, I've really enjoyed a lot. I've seen a lot of variety, and I see that there are a lot of topics that are interesting for me at least, and I think there's just so much variety. It's so nice. Okay, so I decided to integrate some new things into this talk relative to what's in the title, but it will be a talk that doesn't go too deep in any topic, but touches on a few things that I think I've seen at this workshop already, and that hopefully I will see some more of later in the few days. The first part is going to be about cavity QED, and we've seen a ton of cavity magnonics stuff already and hybrid systems related to cavity QED. The ideas that we had in cavity QED are not directly tied to magnonics, but my hope is that some of these ideas can be transferred to magnonics, and then just by presenting the ideas, we can foster some collaborations. And then part two will be on topological bound states, and I know that there are people in the audience who are experts in this topic as well. It might be an opportunity to see some kind of connection there too. So in cavity QED, usually we think of an atom that is stuck inside a cavity and it wants to interact with the electromagnetic field mode. And the Hamiltonian we use to describe this interaction in the long wavelength limit, is this cutting off? Okay, the Hamiltonian we use to describe this interaction in the long wavelength limit is the dipole interaction. Usually it's the interaction between the charged dipole and the electric field, but it could just as well be the interaction between the magnetic dipole of some atom or some excitation and the magnetic field. And the electric field is quantized, so we can represent it in terms of some kind of position operator of a harmonic oscillator, a sum of creation and annihilation operators, bosonic operators. And if we want to describe the interaction with two levels of the atom, then we can collapse that Hamiltonian onto a two-dimensional subspace of excited and ground states in terms of these Pauli matrices. And if we do that, generically, we get two types of terms. One type that preserves the eigenstates of the atom, and the other type that doesn't preserve the eigenstates of the atom. And those two terms are the longitudinal coupling and the transverse coupling. Very often in cavity QED, we throw away the longitudinal coupling for a very simple reason, which is that atoms have inversion symmetry. And if you have an atom that has eigenstates that are invariant under parity, then the position operator has an average of 0, but the transition dipole matrix element may be non-zero between states of different parity. However, if you have a magnetic system, then you might have excitations that have an intrinsic magnetic dipole, and this is very common for magnons, for example. Alternatively, if you have a system that doesn't have inversion symmetry, so if you have a designer system like a quantum dot or a pair of quantum dots, then you can get a situation where you have a non-zero longitudinal coupling as well as a transverse coupling. And what's very important there is that that longitudinal coupling can be controlled electrically. So we looked, for instance, at generating such a longitudinal coupling and a transverse coupling for a spin qubit, a single electron spin, in a double quantum dot in the presence of the magnetic field from a nanomagnet. So just by positioning a double quantum dot at one place or another under a nanomagnet, you can actuate the spatial degree of freedom, which couples to the electric field for that electron. You can actuate that spatial degree of freedom according to the spin orientation, just by virtue of the fact that you've got a magnetic field gradient. And by changing the placement of the double quantum dot relative to that nanomagnet, you can either make the coupling purely longitudinal or purely transverse by turning on or off the effective symmetries of this Hamiltonian. And we did this work together with Michel Pierre-Ledrea in Sherbrooke and his student Danny Lachance-Curion. Danny actually went on to work with Yasu Nakamura, and I've seen his name on a few of the slides. You've probably seen his name on other papers as well. So he did some of these strong coupling experiments with YIG. The longitudinal coupling, even, oh yeah, if there are questions, please go ahead.
So which symmetry do you use to turn off the transverse coupling?
Well, if you have two states that differ by multiple excitations, then they might not be connected by the position operator. So, people who want to have very long-lived ion states often deal in the subspace of the S level and the D level, where you need two powers of the position operator to go from one of those states to the other, because they're connected by two lowering operators for the angular momentum. So it's not necessarily a symmetry, but you can have states that are connected only through a quadrupolar interaction or some higher power of R.
Okay,
Yeah.
thanks.
So you actually derived if some more microscopic model that you project in the lowest states, and then that's how you define this GX and GZ?
Yes, that's what we did in this paper. So in this paper, we really derived it from a more microscopic model of the double quantum dot and the magnetic field distribution, and then you can show that you can get relatively strong values on the order of several megahertz for either of those parameters, GX or GZ. Okay. And at the time, we knew that longitudinal coupling was also something interesting, because at the same time, there was work going on in the superconducting qubit community to understand how to exploit longitudinal coupling for superconducting qubits. And in particular, there was this idea out there to use it for readout. So it's a natural thing to use for readout because often you want measurements to be quantum non-demolition. You want them to preserve the state of your qubit, and the longitudinal coupling is, by definition, something that preserves the state of the qubit. It's proportional to sigma z. Usually, even if we have such a term, such a longitudinal interaction term, if you have a cavity frequency that is large, then this term won't necessarily contribute because when you go into a rotating frame with the cavity Hamiltonian, then you find that you get rapid oscillations, and those oscillations will cancel this out. But you can simply cancel those rapid oscillations by parametrically modulating the interaction in the case where you can tune that coupling. And we heard yesterday from Yaroslav that there are situations where you can tune such a longitudinal coupling for a superconducting qubit coupled to some magnetic system. And indeed, that the longitudinal coupling is a kind of natural interaction for these magnetic systems because the magnetic excitations have a finite magnetic dipole. So if you parametrically modulate this coupling at the cavity frequency, then in the rotating wave approximation, you get a Hamiltonian that looks very, very simple. It looks just like a position operator for your harmonic oscillator times the Pauli matrix for your qubit, excited or ground state, gives you eigenvalue +1 or -1. And so if you look at the time evolution under such a Hamiltonian, we know that position is the generator of translations in momentum. And so you get a translation that goes in the plus momentum direction or minus momentum direction as a function of time, simply dependent on your qubit state, whether it's in the plus sigma z +1 eigenstate or sigma z -1 eigenstate. And this provides a benefit in readout if you do it relative to dispersive readout, because you get direct translation. On a shorter time scale, you get a larger separation of the coherent state blobs that you get for your electric field. Okay, so your electric field will do one thing or it will do the opposite thing with a higher and higher amplitude as a function of time, whereas with a dispersive readout, you take some indirect path in parameter space. And Michael has a question. Yeah. I'm sorry. Yeah, sorry. This picture here is a schematic that shows the quadratures of the electric field, so I and Q, or the in-phase and out-of-phase quadrature. So if you take the electric field, just does either a cosine or it does a sine. If you take the cosine Fourier transform, you get translation on one direction, sine Fourier transform translation on the other. You can also think of these as X and P. Those are two quadratures. Okay, and then the picture on the right is also the two quadratures. So the vertical axis is like the momentum. The horizontal axis is like the position for your harmonic oscillator in some rotating frame. Okay, so if you apply time evolution under this Hamiltonian, this is like a position operator, sum of creation and annihilation operators for bosons. The time evolution operator will generate translations in the momentum direction, so it will just generate a translation of an initial coherent state blob along the p direction. Yeah, sure. Is that okay? Not clear?
It answers the question, but then I'm still clueless on how this helps with readout.
So the way that readout is done for most superconducting qubits is through a dispersive coupling. The dispersive coupling looks more like a number operator times sigma z. And then that acts in combination with the other parts of the Hamiltonian to give you some kind of time evolution for the annihilation operator. Okay, the real and imaginary parts of the expectation value of the annihilation operator give you basically the x and p expectation values for your harmonic oscillator Hamiltonian. And so x and p are going to do one thing or another thing depending on the qubit state. And for a dispersive readout, you don't have a simple translation. You have something that gives you a more complicated evolution. Okay? And the more complicated evolution, it turns out, does not separate the two final states of x and p as fast as a direct translation. So a direct translation gives you a faster readout. I'll try to communicate it in simpler terms. The talk is not about readout, but it uses this idea, and I can make it more concrete. Yeah.
When you are in the rotate wave approximation, do you need to work in the weak coupling regime or not?
Weak in the sense that the cavity frequency is large compared to the coupling strength, yes.
Mm-hmm.
But not weak in the sense that the coupling strength can still be much larger than the decay rates. So usually we call that the strong coupling regime, but not the ultra strong coupling regime.
Okay.
Is that okay? Okay.
Mhm.
Okay. So this idea can be extended, and my student Zoe McIntyre had this very clever idea to extend this notion of controlled motion of this harmonic oscillator, which is really the cavity, dependent on the qubit state. And in particular, if you had a situation where you could create a coherent state wave packet, just classical light, classical pulse of light, send it onto a cavity, and depending on whether your qubit is in the ground state or the excited state, you either get perfect transmission or perfect reflection. Then you can arrange a situation where you prepare your qubit in a superposition of excited state and ground state. And you might get a superposition of having the qubit in the excited state and get perfect reflection of a classical pulse of light, qubit in the ground state and get a perfect transmission of a classical pulse of light. The advantage here is that you don't need to make single photons. You don't need to make exotic quantum states of light. You can simply use classical pulses that can be produced with any laser or microwave source. Or in the case of magnons, it might be that you can make them simply with electron spin resonance or some ferromagnetic resonance. Okay, so now I'll try to make it a little bit more concrete for Michael in the back and for others in the audience. So if I have a cavity is a harmonic oscillator because I just take the energy to be a quadratic function of the electric and magnetic field modes. I quantize that harmonic oscillator, just like harmonic oscillator has p squared term and an x squared term. I've got an e squared term and a b squared term. Quantize that harmonic oscillator. And just like a pendulum is a harmonic oscillator for small amplitude modulations, I can drive that pendulum. I can also drive the cavity harmonic oscillator by applying an electric field and shaking it up. And if my electric field is resonant, so I push on the cavity at the resonance frequency of the pendulum swings up and it gets some kind of amplitude, and then that pendulum will transfer its energy to the outside. So at resonance, a drive will just sort of propagate straight through the cavity, okay, because it does resonant excitation of the pendulum, goes straight through. We also know that if we have a charged dipole, and that charged dipole is oscillating in time, it should radiate radiation. And so if the charged dipole is oscillating at a frequency that is matched to the frequency of that pendulum, the cavity, you're going to ring up the cavity, ring up the pendulum, and then light will spill out on either side. Okay. But now if I have a pendulum and I have two forces that are equal and opposite, that act in phase with the same amplitude, then they can cancel exactly. Okay, so now imagine that you have an oscillating dipole associated with the excited state, but no oscillating dipole associated with the ground state. Okay? So then if you're in the excited state, you have this oscillating dipole, and if it has a tuned phase and amplitude that perfectly cancels the incoming field, then what will happen is that there can be no excitation of your pendulum, there can be no excitation of the cavity, the incoming field will perfectly reflect. But if your qubit is in the ground state, there is no dipole there to oscillate, there will be no counteracting force, and the light will pass straight through the cavity, provided it's frequency matched with the cavity. Is there a question? Yeah.
Just to make sure I understand the picture. When you say there's an oscillating dipole, do you have more levels or just the two?
I'm just thinking of two levels.
But then, what does it mean? You know, if something is oscillating to, you know, to generate some radiation,
Yeah.
it has to go between two levels, right? I mean, when you say the ground state doesn't have a dipole, what do you mean when you say the ground state there's no dipole?
I mean that the dipole moment, the strength of the dipole moment is increasing and decreasing. So if I have a positive charge and a negative charge associated with the excited state, displaced by some amount, then I have a finite dipole. If I move the positive charge relative to the negative charge, I increase the strength of the dipole. If I move them closer together, I decrease the strength of the dipole. So all I'm doing is doing this.
But you know, sitting on the excited state, and the same thing for the ground state.
I want a situation where the ground state would not have an oscillating dipole.
Yeah, in this case, yeah,
It can have a dipole, but it can't be oscillating.
Yeah.
Yeah.
Okay.
So let me try to put it in kind of my words and see if it's actually right.
Okay.
So essentially the way I might think of this is that the index of refraction for the microwave is just going to be different in the ground and the excited state. You have a polarization in the excited state. You have zero polarization in the ground state, although it could be still a polarization, it just has to be different from what it is in the excited state.
Right.
And as a result, the index of refraction is different, and you can therefore tune the cavity such that it would reflect in one case and transmit in the other. Is that correct, or am I off base?
It's, I mean, I think, well, it is, so it's definitely some polarizability, but it's a dynamic polarizability. So
Yeah,
I
but
don't
that's
know
always the case
if you're
for
okay with
index of
that, then yeah,
refraction.
okay, it's
Yeah,
not
I
a
mean, that's what
static
goes-
index.
That's what goes into the index of refraction of finite frequency.
Probably you can think of it like that, yeah.
Okay, great.
But it is not a passive thing, you know. So you're adding energy in principle. You're driving the system, but okay, no energy is produced if you have this perfect interference. Yeah. So indeed, yeah, I think that's right.
So where is this in the Hamiltonian? You're going to show us a place where this is happening so we can picture it?
I didn't write it on the slides because I'm trying to be quick, you know. But I won't get through this talk. That's okay. But I can. So basically, the equation of motion for the cavity is just a harmonic oscillator. The equation of motion of the cavity is a damped-driven harmonic oscillator. Okay? And if you apply radiation on the cavity, that's a driving term, a forcing term, just like one of these guys, you know, this guy. If you have an oscillating dipole in the cavity, that's a driving term, forcing term. And two forces, if they're equal and opposite, can cancel out. That's it. And then the damping is simply the thing that takes the photons from the cavity and takes them out. Yeah. Well, it's not loss per se, because they're still existing in the transmission line in my imagination, but they leave the cavity, yeah. Okay. Now, so here's the setup. It's I'm not writing the Hamiltonian, I'm not writing the Langevin equation, but I told you what it is, so you can imagine. Okay, so if you have an equal matching of this modulated coupling together with the amplitude of the drive matched with the waveform of an input pulse, u of t, then you get this perfect cancellation if your qubit is in the excited state, okay? And then you get perfect reflection because the cavity can never be occupied. You can never ring up the pendulum. So the cavity remains in its vacuum state. If you are in the ground state of the qubit, then you will get perfect transmission provided the input and output rates are balanced, and provided the input tone is narrowband relative to the cavity line width. Okay? So it actually works better for larger kappa, which is an unusual situation. So if you have kappa that is larger, get a cavity that supports more frequency modes, then you can put in a tighter, shorter wave packet U of t. But this allows you now, if you can control your qubit, prepare it in a superposition of excited and ground states, it allows you, in principle, to create this qubit witch path entangled state, where you have an entangled state of your qubit in the one state with the coherent state in one mode, going one way, and the qubit in the ground state with the coherent state in another mode, going the other way. And why is this good? A number of reasons. First of all, you don't need any resonance between your qubit and the cavity. Okay, so you can work with a qubit at gigahertz frequency, a cavity at optical frequencies in principle, but you need to be able to modulate your coupling at a frequency that's equal to the cavity frequency. So you can work in this ultra-dispersive regime where you don't have necessarily coherent transfer of excitations, energy back and forth. You simply do something conditional in the two qubit states through this driving. Second, you only need classical sources of radiation, so coherent state pulses. And in fact, it won't work if you don't have a perfect coherent state. You need something that's an eigenstate of the annihilation operator. If it's not, then you'll end up with noise and this matching condition won't work. Okay, so a regular Fock state or thermal state will not work necessarily. Third, you don't need to be in the single photon strong coupling regime to get strong quantum effects. The reason is that you can simply get these orthogonal modes that are very distinguishable just by using a larger alpha, a larger amplitude of the coherent state. And what you can do with this now is, for instance, you can re-interfere the two outputs of your interferometer on a beam splitter, and then one output of the beam splitter will give you no information. It just gives you some blob that's the same whether you went through one arm or the other. The other arm of the beam splitter will give you some special superposition of the qubit with what's called a Schrödinger's cat state, equal superposition of alpha and minus alpha, two amplitudes of the coherent state, and you can swap that information then to different qubits using known methods, so a parity-dependent phase shift. So you can do a phase shift on your qubit dependent on whether you have an even or odd number of photons. And that allows you to create a long-range entanglement between stationary qubits, provided you do a measurement which is simply a phase-sensitive measurement of the coherent state. So either homodyne detection, where you measure the same frequency, or heterodyne detection. And those are sufficient to generate entanglement at the distance. You can also use this for quantum-enhanced precision sensing, because you've got an interferometer built in with the nature of the state. And so you can measure actually at the Heisenberg limit. So you get a sensitivity, in fact, with this phase-sensitive measurement that saturates the quantum Kramer-Rao bound. It's the maximum sensitivity allowed by quantum mechanics. It's also something that was not known for this type of states until very recently, I think. It was previously believed that you needed number-resolving detectors or some kind of parity measurement at the end, but we showed in this paper that you don't need that, provided you measure a differential phase rather than an absolute phase. Okay, are there any more questions about this one? There's a question from Yaroslav.
Just a minute. I can give you the microphone.
All right, so the whole idea of cancellation is, I guess, because you assume that the dipole is a perfectly harmonic oscillator.
The dipole, well, in my language, the dipole is simply it creates the coupling strength, but you're saying, so the oscillator for me is the cavity.
Yeah, okay, so again,
the dipole is the coupling strength. The coupling strength is proportional to the charge dipole, which is associated with one of the eigenstates of the atom that I'm dealing with.
Right. Maybe we can go back to this cancellation picture.
Yeah, this one or this one?
Yeah, like this one is probably easier. So the drive is always harmonic.
Yeah.
Now it's perfectly oscillating dipole should be harmonic for that.
So the drive is also So the drive is the electric field is a function of time. So there's some waveform. When you say it's harmonic, I'm not sure that has meaning. So it's just it's a force, right, in the equation of motion.
Yes. Let me ask the question because I didn't yet ask the question. Okay. Would it be? I thought that could be a cool system to explore non-linear behavior of the oscillating dipole, assuming another one is linear. Maybe I misunderstood things.
Okay.
But is it something like that feasible?
I think this would break down if you have a nonlinear cavity.
Okay.
So for me, the harmonic oscillator is a cavity. It's the pendulum.
Okay.
The pendulum is the cavity. The other two things are simply parametric modulations. So I have a parametric modulation due to an input tone, and I have a parametric modulation of the size of the dipole associated with the excited state.
Okay.
But if you did have some nonlinearity in the cavity already, that would show up in a deviation in this equation of motion. That's right.
Yeah, because if you break this perfect cancellation, then of course you are just sensitive to these fine details.
That's right. It might be a very good sensor for nonlinearity in your cavity. Yeah. Okay. And then you can detect whatever's around. That's a very interesting point. Yeah.
Okay. Thank you.
Yeah. Okay. So now I'll go to the next part of the talk on topology, and I know that there are experts in the audience on topology, but I wanted to go through some of the basics for the people who are non-experts, and then we can quickly see how that relates to what I'm talking about. So if we just have a tight binding chain, then we know how to solve for the energy spectrum of this tight binding chain. It's translationally invariant, and so you can Fourier transform, and you get a set of Bloch waves. And then the energy spectrum is a continuous function of k, provided you have an infinite system with periodic boundary conditions. You know that also the states are periodic in k. And because they're periodic, it means there's a constraint if you require that the states themselves be continuous. But that constraint doesn't give us any kind of non-trivial topology if we have equal sites. And so we need to introduce some difference between sites, and most of you have seen this alternative, the Su-Schrieffer-Heger model, where you have an alternate tunnel coupling, VV prime, on every alternate site. This is again a tight binding model that's translationally invariant, but invariant under translations of 2 lattice sites instead of 1. And so again, we can write down Bloch waves, but because there are 2 lattice sites per unit cell, we know that we need a 2-component spinner to describe the eigenstates. And that 2-component spinner will have a non-trivial phase in general associated with it, with one of the components. And that allows us to identify a quantity that necessarily has to be quantized by virtue of the fact that the eigenfunctions themselves are periodic over the Brillouin zone. So this quantity in this simple example is the winding number. It's just the number of times the phase winds by 2 pi and going across the Brillouin zone. Okay, and the winding number is 1 for one ratio of these tunnel couplings, if V prime is greater than V, and it's 0 if V prime is less than V. Good. And we know that if V prime is different from V, we have 2 different hopping amplitudes, we end up with an energy gap. You've all learned this in solid state physics, that's proportional to the difference between V and V prime. And in general, whenever we have a winding number, we're going to have an energy gap. And in the situation where we have V equals V prime, we know that the winding number is undefined because we've gone back to the old tight binding chain. And in this case, the energy gap has to be 0 because we can describe the energy spectrum simply by folding down into a smaller Brillouin zone for the doubling of the lattice constant. Okay, the fact that there is a state at 0 energy when V is equal to V prime means that there must be some kind of 0 energy mode if we take one bulk spectrum and try to continuously deform it into another bulk spectrum associated with a different winding number. This is the bulk boundary correspondence. So if we were to introduce a situation where V and V prime alternate up to some point, and then we create a domain wall where V and V prime change their roles, then we must have a situation where the winding number is 1 deep in the bulk on one side, and the winding number is 0 deep in the bulk on the other side. And at the interface between the two, if we're going to have a continuous deformation of the energy spectrum, it has to be that there is a state at 0 energy. And it turns out that that state is a bound state, so it cannot penetrate deep into the bulk of the other materials because, okay, we're not allowed to have states at 0 energy down there. And you get these so-called Jacques-Rebbe bound states in many different scenarios. So not just in the 1D tight binding chain described here, but also in two-dimensional systems, where the winding number can be replaced by the churn number, say the number of times the effective spin, or the spin will wind the Bloch sphere in traversing the Brillouin zone. Okay, and then these bound states underlie things like the quantum anomalous Hall effect. So if we have a magnetic field in the presence of a 2D topological insulator surface, the surface of a 3D topological insulator, that has a Dirac-like spectrum, then the magnetization sort of produces a gap, an energy gap. But in order to go, and then the states associated with the lower band or the upper band have a non-trivial churn number, a non-trivial winding. But to go from inside the bulk material to outside where everything is trivial, we need to have a zero energy mode at the edge, and that edge can carry a single quantum of conductance. And so that's what gives rise to the quantum anomalous Hall effect. And we can take that further and think about what happens in the case where the magnetization changes sign. So if the magnetization goes from all spin up to all spin down at some domain wall boundary, then the churn number will have one value on one side where the magnetization points down. It will have another value on the other side where the magnetization points up. And at the interface, you get a bound state in the transverse direction. But along the domain wall, you can get propagation. And the propagation itself will be chiral because the momentum will be locked to the spin if you have a definite character of the spin-orbit coupling. Here it's Rashba-like. Okay, and these chiral bound states, they can only carry current in one direction because they only have k-states associated with one orientation relative to the domain wall for down-up versus up-down. And there is evidence of these domain wall bound states being produced in experiments where we cycle the magnetic field. If you go up and down with the magnetic field, you can see magnetoresistance changes. And this magnetoresistance change has been attributed to the formation of these domain walls, which can carry extra quanta of conductance, and then the destruction of the domain walls as you move from, say, a state that would be stable at all spins up to a state that would be stable at all spins down by going from large negative magnetic field to large positive magnetic field. So this is the picture. If you've got some kind of sample, the imagination says, okay, well, if I apply a magnetic field, I favor a state at low temperature where all the spins are pointing up. If I have a magnetic field in one orientation, and then if I change the orientation of the magnetic field, my system wants to find the state where all the spins are pointing down, but it can only do so through the production of domain walls. Some of those domain walls will extend across the system, and each of those will carry one quantum of conductance. Okay, so this kind of thing produces a characteristic hysteresis pattern that looks like a kind of butterfly. So you go up on one side, and then you go down, and then you come back on the low conductance end, and then you go up again and down. But there are other plausible explanations for this kind of hysteretic behavior, and it's difficult to rule them all out. So one obvious one for this crowd is that you could have some kind of spin valve behavior, where you've got a bunch of domains that are counter polarized, and then as they change their orientation, you might have a change in the magnetoconductance just from the spin valve effect. Another option is that you could have some kind of weird paramagnetic cooling going on if you've got paramagnetic impurities, or you could just have any other kind of magnetic cooling cycle through the magnetic field going up and down. That might lead to a change in the local temperature, and if you have a temperature-dependent conductance, then it can be hard to rule out the possibility that your conductance is sort of just following the temperature that you're changing. So it would be useful to establish some kind of definitive experiment for this type of situation. Is there a question already?
But then before you move on to this next topic of what would be the experiment, actually, if you are really able to establish this churn number in terms of magnetization, that's actually my question. Because we know the churn number in terms of electronic states and Barry curvature and so on, but how do you define and compute that in terms of this change in magnetization, because then you have a theoretical, definite
That's exactly right.
marker.
Well,
then you can go and try to measure these things. But
I don't know if you're making the same point that I'm making, but you can have a theory that is completely internally consistent and that shows the experimental result, but there could be 6 or 7 other theories that are totally different that are also consistent with the experimental result.
Exactly.
And
but
might
then
be
if
plausible.
you do have, if you compute this Chern number, then you also have something else to offer.
Well,
right? No, I know it's topological because I have this topological invariant, which is non-trivial, that acquires a non-zero value, and it is, at least from the fundamental point of view, a definite marker of topology.
Okay.
So actually my question is, what is the topological invariant here?
So the topological
this
invariant
number
is a
in
Chern
terms
number
of magnetization.
It is a Chern number associated with the bands, and it will be different if you calculate it here with one orientation of the magnetization relative to here with another orientation.
But it's just that Chern number that we know from TKNN.
Yeah, it's the same Chern number, but because you change a topological invariant, there's a bound state at the interface at 0 energy, and that can carry a current. And so right now, many people use the evidence of the change of the sign of the Chern, or the change of the Chern number. They say the evidence is, well, the fact that we've got quantized current. So if you see a quantized anomalous Hall effect, that's a good indicator that you have a well-defined Chern number. In experiments done on materials like samarium hexaboride, the one that I showed before, it's hard to establish that you have a quantized conductance. So the conductance sort of does one thing on the upsweep and another thing on the downsweep, but on average, it's doing something between the 1 and 0 conductance quanta. They tried to show in that experiment that they sort of thought they saturated at 1 as a function of temperature, but the saturation happened and then it was non-monotonic. So I think there are still questions about whether they can get definite quantization of conductance with that experiment, but it's an old experiment. I don't know if I'm answering your question. So it sounds like you're saying the same thing that I'm saying, which is that there are actually multiple ways of interpreting.
I'm not sure. My question is what's the recipe for the Chern number in this in this framework of where states are defined, or
well, you have to write a Hamiltonian, right?
Magnetization.
You write a Hamiltonian in K space, and then you find the eigenstates, and then
okay, so
it's very similar to the winding number that I showed, which, I mean, you know how to calculate a Chern number, maybe? So it's the same procedure. You calculate the eigenfunctions in momentum space, you calculate the Berry curvature, and you integrate over the Brillouin zone, and you get a number out.
That's how it's
the same...
That procedure.
Yeah,
okay.
Sorry.
One more question.
So can you go back and to the experiment? You showed the histories, yes.
Yeah.
How do they actually know that this is actually seeing edge states within the sample and not just bulk states?
Yeah, they really don't know.
They don't know. Where is the Fermi energy and things like that? They have no idea.
I think there's disorder. It's a bit uncertain. Mm-hmm. But this is an older experiment, so it's I have not checked carefully that things haven't been heavily refined in this material already, but I think it was very uncertain at the time, and this is roughly when we started doing this work.
Because at some point we met, today in the car we talked about Gerson for his thesis. He studied, we have a PRL on this, where people had seen the spikes and hysteresis in two-dimensional electron gases, and we identified this with quantum Hall ferromagnetism in the sample. Right. And
I have another reference from Gerson coming up, but yes, I now remember that work, but I didn't include it in this talk, I'm sorry. But he did other related stuff that I'm going to show in a moment. Yeah. Okay, so I should probably accelerate a little bit to make sure I can get through, but not too much. So we wanted to try to think about whether it was possible, as everyone is asking the question, whether it's possible to actually establish that this hysteresis is really due to domain wall bound states. in hopefully a more controlled experiment. So this is sort of coming halfway in the discussion we had 2 days ago on hybrid systems, where people were saying, okay, theorists have to give us the limits and tell us, when things are valid and when they're not. We have to sort of meet halfway sometimes and do a different experiment where things can be controlled. And then the other interesting question we wanted to address was whether we could understand the mechanisms for dynamics of domain wall motion. And I know there are people here who've worked on this a lot. So there has been quite a bit of work in the past on sort of driving the dynamics of domain wall motion through the current, so that you can get a spin transfer effect. And I think, so I think So has done some work on this, and then there have been others who worked on it as well, where the current that you drive, because it's spin polarized, can actually transfer angular momentum to the ferromagnet through backscattering, and then you actually get the kind of conversion of the domain wall, or movement of the domain wall, just due to the spin transfer effect. But it's also possible, if you have a system like this, say decorated magnetism on the top of a 3D topological insulator, it's possible that you can have environment-driven dynamics, where you just have incoherent processes for excitation and relaxation, dumping some amount of energy into the system or accepting some amount of energy from an environment, delta U. And so we wanted to think about that second scenario. And then you can think of this experiment that I will show you as a way of probing that type of dissipative dynamics, which could eventually tell you about how magnetic systems lose their energy, or how dissipation occurs. So we wanted to get rid of all of the problems with the edges, and then we went to a Corbino geometry, where we know that the conductance should be due only to these domain wall bound states that are produced through spin flips, not at the edge of the sample. And in this Corbino geometry, we also simplified the problem drastically by thinking about a 1D chain of spins. So you can make this 1D chain of spins in principle just by decorating the surface of a 3D topological insulator with magnetic impurities. It doesn't have to be some intrinsic magnetic material. And then if you orient a magnetic field in one direction, it will favor a ferromagnetic state with all the spins pointing, say, up. And if you change the direction of the magnetic field, it will energetically favor a state with all the spins pointing down, but to get there, it has to flip at least one of the spins. And in the case where you sweep the magnetic field very slowly, then it can only flip one of the spins, and then that spin will energetically favor producing more downspins and more downspins until the two domain walls annihilate at the end. And the signal that you would see, if you look at the conductance between the source, the center conductor, and the drain, the outer conductor, the signal that you would see is a jump in the conductance at the coercive field. So if you compensate the exchange coupling associated with which you have to pay for, if doing a spin flip with the magnetic field energy, then you can allow this first spin flip, and then all the spins will flip on some time scale that's determined by the equilibration with the environment. Okay, and then the message here is that you can actually predict the shape of that butterfly hysteresis curve, assuming that you have some well-defined dissipation mechanism. And in this case, if you just sort of take a power law dependence, which is common for microscopic mechanisms due to the density of states and the behavior of the coupling with the energy, you can actually predict the shape of that curve, and then, for instance, the maximum of the curve depends on the velocity of the sweep of magnetic field, and then this exponent eta in the spectral density that enters into the relaxation rate. Okay, and then if you wanted to, if you were really ambitious as an experimentalist, you could make some segmented electrodes, and then you could actually see evidence of the chirality of these modes. And so you would see that modes would produce conductance in one direction at one point in space and another direction at another point in space that would change as a function of time, eventually annihilating. And so you could just plot out this kind of picture of where the conductance is finite, forward or back, as a function of position. And then, okay, so then we moved on to another question, which is related to what you were saying. So you and Gerson worked in the past on this ferromagnetic quantum Hall systems, and then Gerson went and worked with Daniel Loss on, for instance, using these bound states not as conductors for current, but just producing some isolated, well-defined states on little bubbles of domains. So if you have a little domain with counterpolarized ferromagnet on the surface of a topological insulator, then the domain wall will produce a kind of localized state, and that localized state can then be used to support a qubit, and you can try to do quantum computing with these things, and that's what they proposed. And the problem there, of course, is that the domain will dissipate at some time scale. And if you want a very long-lived magnetic structure, another option is to use a topological defect in the magnet, a skyrmion. And the skyrmions should have a much longer lifetime because they're topologically stable. And so these authors looked at similar bound states attached to skyrmions. And we started thinking about that. And then I looked at this paper from Skyrm, I guess, Tony Skyrm. So he gave the name to skyrmions, and he wrote this paper. It's the introduction of skyrmions to the world in order to understand some nuclear physics problems. He found basically the first soliton solution to some field equation. And he's a sole author on the paper that introduced the skyrmions, but at the very end of the paper, he says that he's indebted to Mr. A.J. Legat for carrying out the calculations reported in section 3 while on vacation as a vacation student. So as an undergraduate, a young undergraduate, A.J. probably Leggett, apparently did the numerical calculations to understand that skyrmions are repulsive at short range on very basic principles, and that they're therefore stable as individual particles, and they won't collapse into sort of falling in on themselves. Okay, so skyrmions are repulsive for a very simple reason. If you think of a Bloch skyrmion, where the magnetization sort of winds perpendicular, in plane perpendicular to the radial vector, then two Bloch skyrmions that come close together will have two counterpolarized magnetizations in plane. And if you have a ferromagnetic coupling, then that will be unhappy because they'll point in the opposite direction. But the skyrmion has a spin that points out of plane in the center along the up direction, and as you go toward the outer edge, then it points in the opposite direction. And the skyrmion magnetization actually covers the whole sphere when you cover the plane, and that's what makes it a topological defect. Okay, so if you calculate the free energy for a skyrmion, you will find indeed that it sort of wants to go far and farther away, so these skyrmions will want to repel. But as I mentioned, you know, the magnetization out of plane changes sign, and so you get this effect of getting a topological bound state at the edge of the skyrmion that's bound to this sort of interface between having a positive out-of-plane magnetization and a negative out-of-plane magnetization. And so you can think of a skyrmion as being like an atom. It's like the hydrogen atom, or it's more like the nucleus, and it binds an extra charged particle, like an electron, to this little bound state that lives at the edge. And this was studied by Hilary Hurst and others a few years ago. But if you can make a single atom, then you can also think of making molecules. And in particular, the molecules can provide a binding energy. So if you allow two skyrmions to come close together, there is a separate length scale associated with the bound state of electrons that are bound to that magnetic texture, and the length scale of the healing length of the magnet. And provided the healing length of the magnet is shorter than the length scale associated with the electronic bound state, if you have one electron for two skyrmions, it will form a molecular orbital that has lower energy when the two skyrmions are close together than when they're far apart. And so you get a kind of attractive interaction from the molecular binding opportunity, because you distribute the electron over more area. But you, at the same time, have this repulsion at short range, which is just like we have for atoms and molecules. Okay, and then you can sort of explore the phase diagram and see, in order to produce this bound electronic state, you need a reservoir of electrons. And so if you fix the chemical potential of the reservoir of electrons at a large enough value, you always have electrons available for binding, and then they can always stick the skyrmions together. But if your chemical potential goes below some threshold, which is the individual ionization potential of an individual skyrmion, then you get a kind of metastable state or hysteretic behavior. So if you start in a stable state, this green picture, and you go into this hysteretic orange-yellow region, you will stay bound. But if you start in the unstable state, far separated, and you move to the orange region, you will want to stay far separated, okay, until you have some activation process and you get to the local minimum. And in the blue-purple region, you have a kind of metastable bound state that can form. And this is all classical, and this name of this workshop is something about quantum magnonics, so we should do something quantum as well, okay? So we know that if we have classical spin textures, classical magnetism, then we can bind electronic states to those spin textures. But what happens if we now have a spin wave or a magnon mode? Can we bind electrons to these delocalized magnon modes as well? So Ivan Martinez, who's sitting over there, looked into this problem a couple of years ago. So if you have a single spin flip, it produces two domain walls, and you can get two little bound states there. But if you have a magnon, it's like a coherent superposition of spin flips all over. So you can think of having a coherent superposition of bound states all over. And you can ask yourself, how stable is this? So it's very easy to sort of numerically put this on a lattice. You can take that Dirac-like Hamiltonian with a Rashba interaction on the lattice, and assume that you get some particular distribution of the magnetization as a function of position. So if you have a single spin flip, you get the picture on the left for the magnetization profile in real space for, say, a single magnetic impurity that is flipped relative to its neighbors. And on the right, you can see what the bound state looks like. The color scheme gives you the probability density for the electron that's bound to that state, and then the arrows give you the velocity distribution, because that electron has to be spinning in a chiral way. And then you can go ahead and do exact diagonalization of this system, and you see that even for finite systems, you get these well-isolated states. They're not quite at zero energy, but they're isolated from the continuum band. And then you can ask the question, how do I measure these? What is the probe that can excite such a thing? And it's a bit unusual, because it doesn't require just a spin flip. It also requires a charging event. Okay, and so you have to provide the system with both the opportunity to be excited with a transverse field at some frequency that might be resonant, and at the same time it needs access to a reservoir of electrons. And so we looked at this situation where maybe you have a reservoir that's available at time 0, where the band of electrons in the reservoir is full, but the other bands are empty. And this is important for something that I will mention at the very end. So imagine the other bands are empty, and you suddenly populate this reservoir. This can be a non-equilibrium reservoir. You just populate some band with a bunch of electrons. If those electrons can tunnel into this bound state, then that provides the opportunity to create one of these excitations with a transverse magnetic field. Okay? And you can solve that problem exactly. If that band of electrons in the reservoir is full, you can solve it exactly. It looks identical to what's called a Wigner-Weisskopf problem from atomic physics. It's just, it reduces to a two-level system. You can sort of find the exact solution for, say, the spin susceptibility. So provided you hit the system with the right frequency of transverse field fluctuations, you should see a little spike in the transverse spin susceptibility corresponding to producing one of these excitations at an energy where a normal magnon would be forbidden and the normal electronic bound state would be forbidden. And in particular, if you sort of tune now the energy offset on the horizontal axis between the bound state and the reservoir, and you tune the frequency of modulation, you can get one of these wonderful pictures that shows hybridization, something we all like, right? So actually, if you tune this reservoir relative to the oscillation frequency, you can get hybridization between what would be the bulk regular magnon band and what we call the Jakiv-Rebbe magnon, so associated with this electronic bound state. And in fact, because the Jakiv-Rebbe bound state can have lower energy than the regular magnon, you get a quantum phase transition at a very special value of this offset to a state that is unstable to the production of these Jakiv-Rebbe magnons, provided you give angular momentum and you allow for it to absorb an electron. Okay, so you should get a proliferation of these things beyond that, but we just calculated to where it just gives one. Okay, so this would be a nice signature if someone could set up a situation where they can see this. It would be a nice signature of hybridization between a highly non-trivial topological bound state and a quantum magnetic system. Okay, so I'll just give a quick summary again. So I've shown you that this longitudinal coupling, if it's modulated, can be used to generate Witch path entanglement with a qubit. We talked about this idea to sort of measure the magnetoresistance and use that as a probe of local relaxation mechanisms. And we showed that you could get an exotic phase diagram of sorry, this is an exotic phase diagram for the skyrmion molecules. And then finally, we can do everything in the quantum regime, and also get a nice experimental signature. So thank you for your attention. Thanks especially to Ivan, who did the work on the last slide on the last project, and he'll give another talk, I think, tomorrow or Friday? Tomorrow. Friday, okay. And Zoe McIntyre, who worked on the longitudinal coupling project. So thank you.
We have time for some questions. Thanks.
So this last part, when you showed this, so you have skyrmions. Can you go back to the picture you have?
For skyrmions?
Yes.
So these are not skyrmions. Those are just the velocity.
Like
I know it's confusing. This is the velocity profile for the electrons.
The next one.
Okay.
What was the next one?
This one is also the electrons. It's just a periodic version of the last one.
Ah, okay.
So where you see a periodic distribution. So we used, Ivan used periodic boundary conditions over a supercell that contained many of these magnetic atoms.
So those are not topological structures in the sense that they're skyrmions.
They're topological bound states.
Yeah, sure.
They're topological from the perspective of the electrons, but not from the perspective of
I'm wondering, because we got pictures like this when you take, say, we're proud of this paper, actually. Poliana was involved in this, is where you have a 2-DAG system, but with 2 subbands, and then you have a persistent spin helix along one direction and another one perpendicular to it. Okay. So the density is a skyrmion, and we got skyrmions without interaction. So I was just wondering here, but it's not the same thing.
No.
No. Okay.
No, I don't think so.
More questions?
So you had this Corbino disk discussion where you modeled the magnetism in the middle as a spin chain, right? 1D.
It's just an Ising spin chain.
So I was wondering, have you thought about what would happen if you make the width of that chain wider?
Yep.
Because that models the actual setup, I guess. The experiment.
Yeah. So I mean, okay. So we were thinking in the limit where the length scale for decay of the evanescent modes from the leads into the region there is sufficient to give overlap with only one magnetic impurity at a time, and you can quickly estimate what that would be. So if you're saying you want to work with a lattice that has an ordered array of these spins, and then just put this on top of that lattice, we know the length scale where you would have to go. I would guess that fabrication at atomic length scales is not going to work, and you probably have to do this at,
but if you make
greater
it
than
wider,
nanometer, tens of nanometers or hundreds of nanometers.
I mean, if you make it wider, you could get domains now again.
Yep.
Made up of these impurities, right? Then you could have edge states. And
that's
that
right.
edge state could have a long length scale, right? That's a propagating mode that can actually reach from one side to the other.
Yeah.
And some of them can kind of curve back in, right? Depending on the shape of the domain.
Right. So this is something we wanted to avoid in our analysis. But yeah, you're right. Indeed, if you did this on a regular material, you could have all these kinds of loops.
Yeah. So is it kind of like a percolation problem, or
it
like
becomes
does it map
a very
to some
well, it's I guess it's really complicated if you produce more than just the 2 domain walls here. So you're talking about a situation where you can think of even spirals or whatever of domain walls.
Yeah, like now the domain, the edge states can make various shapes, right? Not just a single line that goes from left to the source to the drain, but now some can go back.
Right.
But you have to, I guess, do some sort of averaging over all possible types of shapes.
Yeah, we would have to. We just wanted the idealized model but that's a very good point. If you want something that's more realistic for that scenario, definitely you'd have to worry about a much more complicated situation.
Thanks, Bill. I think I missed your bath. So you have like the topological states, the bound states, and then you're saying that you're coupling this to a bath that has one band fully filled.
Oh, okay, that one, yeah. So it's a formal requirement for the exact calculation that this band be fully filled.
Right.
Because otherwise you have higher order processes that are complicated to deal with.
Gotcha.
You can still do it in weak coupling for a partially filled band, though.
Right, but in terms of your next result, is this the magnonic band?
No, this is just an electronic reservoir. So it's filled with electrons. So this Jacques-Rebbe magnon it's a charged magnon. It requires both that you flip one spin, like a magnon, but you also have to provide one electron to bind to this thing. So in addition to requiring some source of angular momentum, like a transverse field, you also need some source of electrons. And that reservoir, the blue thing, is just a source of electrons charge. And then the transverse field is something else.
Does the reservoir also give rise to like broadening of the levels?
Yes, this is included in the calculation because it's exact, but we took a limit, I think, where the broadening was just so narrow it didn't matter.
Thank you.
You're welcome.
We have time for one more question. Okay. Oh, Mariana.
So if you could go back to the slide which you used to answer Eggy's question. Yeah.
This one?
No, the one with the velocity field.
Well, this is the velocity field as well, but
that
they're
one.
both velocity fields.
It's the same, right?
Yeah, the other one is just a single unit cell.
It's
and then this is a supercell that contains many of these magnetic.
Can be that one. So you said that this is the topological state. So let me just confirm that I understood this. You said that the topological state is not the magnetic background, but the electronic state that's binding to this magnetic texture.
Yeah, exactly. So in this case, there's no topology associated with the magnetism.
But with the
electronic bound state. Yeah.
And this velocity field is
the velocity of the electron moving around the magnetic texture.
It's the signature of this electronic topological state.
Absolutely. If you could measure that velocity field, that would be the best measure. It's probably very hard to reproduce such a velocity field if you don't have a similar type of state.
Yeah, I can see that it has like a nice topological structure, but can you elaborate a little bit more on how this is? How can you assure that this is a topological electronic state? That's the DOS to the left.
I would say, okay, so we know that the model itself gives these topological bound state.
It's a bound state.
At the interface between two different magnetic domains, one with spin up, one with spin down.
Yeah, it's a bound state, but...
And then if you have a magnon, you flip the spin with equal probability or equal amplitude at every site, right? So it's almost like having a superposition, or this is exactly like having a superposition of having a little circulating current around each spin flip in superposition. So imagine creating a coherent superposition of having a circulating current here, circulating current here, circulating current here.
Okay.
So just measuring the velocity field is not proof of topology.
Yes.
But it would be a strong confirmation of the model. And the model has a topological bound state. So that would be the argument that I would make.
I'm not following the reasoning, I think. Yeah, so to the left, are we seeing the density of states as a function of energy?
Yeah.
So shouldn't we expect a peak exactly at zero energy to confirm that this is
for an infinite
looks
system?
More like a topological bound state?
I think there's a finite energy associated with the size of the domain wall bound state. So this E0 is largely set by the size of where the magnetization goes from positive to negative in the vicinity of the flipped spin. So it's not zero, but it can be much less than the gap. So you would see no states in the gap, ideally, if you didn't have these topological bound states. But you do see a state in the gap, and the presence of a state at that energy is also an indication that the model is correct. And
so the gap is like the energy difference between the second to the left to the
Yeah, roughly between the continuum bands, you would just have the states that would be available if you didn't have this special.
But that's my point. Where do you define what's bulk bands and edge bands or bound bands, bound state bands in this case?
Well,
if you don't have
you can see that this state is isolated from that, but it's a finite size system, right? So in principle, all of the states, you know, if you go to a larger and larger system, then you get a bigger and bigger separation with a pure continuum that stops, and then you have isolated states. Just single well-defined states.
So did you check that? So enlarging?
Ivan has checked increasing the size of the system, and you can see that it becomes more continuous. There are other things you can do analytically that allow you to see that that's what should happen, yeah.
Okay. Yeah. Okay, thanks.
You're welcome.
Still related to this, could you have some kind of trivial bound state that would mimic this, or can you rule that out?
Well, you can, but so that's why I said, so I would think that you want to correlate a few different measures. So just seeing a state at that energy, I agree, is not really strong evidence. But if you correlate having a state in the middle of the gap with the specific velocity profile that's predicted from the theory, then that would be a confirmation that at least the theory seems consistent with the experiment, and then that would give me more confidence that it is indeed this topological state.
Okay, thanks.
No, we know the topological invariant. That's not going to tell us. So we know that it's one value inside and it's one value outside of the region with, you know, with positive magnetization or negative magnetization. It's easy to write it down, but it's a bulk quantity, right? So we know that number. We know it changes sign in the model, and that doesn't help you do the experiment.
So just to make sure, this is just it's topological because this is Jackie Rabi, you know, kind of bound state. That's topological, period. And of course, when we see this nice picture, you think of the topology in, you know, with at least my sick mind thinks in terms of a skyrmion or some texture, but the texture is not topological. Right? This turns out to be like that because you have a magnon. Right?
Well, there's a winding of the velocity field, so I'm sure you could define a.
But then, you know, but this is the same as you know. Are you saying now the winding? I mean, you cannot use it twice, right? It's topological because you have already something that gives you. It's a domain mall. It's the Jackie Rabi, so it's topological because of that. Now, are you saying that this winding is also something that can be used to characterize that?
Okay, so the reason topology is interesting, from my perspective, is because you have this strong requirement in some situations, like in the thermodynamic limit for an energy spectrum, that everything be continuous. And then if you have certain quantities that involve periodic functions over that continuous periodic space, then they can only take on very specific values, right? And then so small deformations should leave those things invariant. That's what's interesting about topology. I don't know if the winding of this velocity field has that feature. It could be that I can just deform it and it doesn't really change things. Like I've introduced some disorder, maybe it looked completely different. I have no idea if this has robustness to that. So I don't know. It's true that it does wind, but it doesn't mean that it necessarily has robustness.
Perfect.
The discussion is quite interesting, but I think we have to stop now. Let's thank the speaker again.
Thanks.